normal finite strain of a fiber. The Lagrangian strain tensor quantifies the change in length of a material fiber and the angles between pairs of fibers in a deformable solid. It is used in calculations where large shapes are expected. To visualize the physical significance of this Lagrangian tensor, Lij, suppose we mark out an imaginary tensor fiber with a very, very short length L0 on the formed configuration. You see, this is L0, this is the L in the deformed configuration. Upon deformation, the fiber increases in length to L is equal L0 plus delta L. This is L. Define, you see that's important, define the finite normal strain of the fiber S. L, this is unit vector Ni, you see, is equal delta L of L0. This can be written as L divided by L0 minus 1. Now, show that the normal strain is equal to the square root of Ni dot the tensor G defined in the last lecture dot Ni minus 1. B, calculate the normal, this case, okay, the normal strain L in the direction of E1, in the direction of E2, in the direction of L and E3. You see this E1, E2, and E3. In terms of Lij, Lij is this equality here, in which is written down there. And show that Lij is 1/2. You see that's important here. This is capital J. This is J transpose. You see? This is J transpose. And this is J times J transpose. J times J transpose. A. The normal, in this case, the normal finite strain is equal, now a square root of Ni dot G dot Ni minus 1. As we pointed out in the last lecture, the importance of this del L of del L0 is equal L divided by L0. This L divided by L0, L divided by L0, this is dx, d is small x, that is capital X. This is the famous stretch ratio. You see? Ratio. That's a very important. Now, let's calculate then. You see L square is dx is square. You see, this is after the deformation. This is L over there. This is equal dx dot dx. This is a scalar quantity, okay? Dimension of its square length. See? This is equal, as we saw last time, dx dot, now this is f dot, let's write down here first. Okay, let's do this is better, okay? Now, let's write down here, dx is equal, this is the deformation gradient, in this case, dot dx, see? Now let's substitute over here, so this will be L square is equal, you see, this is a transpose of the small dx, this is equal dx, in this case, let's put here, the X transpose F transpose F dx. You see, this what we call the G, the second order tensor. This is symmetric because F transpose times F is a symmetric matrix. So this is equal L square will be equal dx dot G dot dx. You see? Now, let's calculate, in this case, L square divided by L0 square. You see, because L divided by L0 is the, in this case, the stretch ratio. This is square of the stretch ratio. So this will be equal dx dot G dot dx divided, let's put here, divide by L0 square. So this is dx square. This is capital dx square. We can write here as dx divided by dx, this is L0 dot G dot dx divided by dx. This is L0, this is L0. So the stretch ratio, the square of the stretch ratio L of L0, you see. Now, you see dx, the vector dx, this is a vector dx right here. This is the magnitude, but the vector dx, I write over here. Let's see, dx is equal the unit vector nu times, this is the same of nu times L0. You see, this is a vector dx. Now, dx divided by dx, so this implies that dx, the vector, divided by the magnitude is equal the unit vector. So this is a unit vector. Let's put here squared. See, this is the unit vector dot G dot the unit vector. Now the stretch ratio L divided by L0 is a square root of nu times the second order tensor G times nu. Obviously, the finite normal strain, you just subtract 1. So L, let's write here, L in the direction nu is equal square root of nu dot the second order tensor nu minus 1. You see, that's what's written there. This is a particular case of this general formulation. This is the stretch ratio minus 1. Now let's apply here. You see, this is the x1 direction. This is x1 direction. This is x2 direction. And this is x3 direction. Now let's apply this L E1, the normal strain in the E1 direction. This is equal, now the square root of the unit vector nu. Okay, nu here is E1. You see, because I'm interested in this x1 direction. So this will be E1 dot G dot E1 minus 1. Let's calculate E1 dot G dot E1. You see, in this x1 direction, the unit vector nu, you see, this is equal U1, because the magnitude, okay, of dx, this is L0. You see, this is L0, and the vector dx is dx1 u1. Actually, let's write here, dx is equal dx1 e1 plus dx2 e2 plus dx3 e3. Let's put this sign here. You see? This is 0, this is 0. So vector dx is dx1 e1. So you cancel here, it is e1. Now, let's do this. This is a scalar quantity, okay? E1 dot, the second order tensor G dot E1, this is a scalar quantity. So, G is F transpose times F. You see, F is partial derivative of a small xi related to the deformed configuration with respect to capital Xj related to the undeformed configuration. So this is the matrix Fij. You see this Fij. It's written over here. You see, the I is equal 1, 1, 1, 1, and the sum on J is 1, 2, 3. Partial I is equal 2, that's the second row. I is equal 3, that's the third row. But the F, the transpose, you see, that's the first column. You see, that's the first row, first column. Second row, second column, and third row, third column. You can see clearly, for instance, G, let's put G12. You see, G12, this will be this second row times the second, this is the first row, first row times the second column. You see, the first row over here, you see a sum. You see, this is sum. Let's put here the first row, 1, 2, and 3. Now, first row times the second column. You see, 1, 2, and 3. You see, there is a sum. You see, we can use Einstein notation. This 1, 1 plus 2, 2 plus 3, 3. So G12, this will be, in this case, okay, now, there's a sum you can write over here, partial of xk with respect to x1, let's put here, x1, now partial xk respect to x2. You see clearly, you see. Now, this is the first row times the second column. You see the number 1 over here, you see, first row 1, 1, and 1. You see, this is 1 over here. You see, this is 1 here. Now, times the second row. So the second column, this is 2, 2, and 2. So this is 2 over here, and this is 2. It's quite easy. That's why we can write Gij, look, I'll erase here, you see, Gij, I put I over here, and J over here. See, this is Gij. That's clearly, you see. There's a summation, the Einstein summation. K is the dummy index. I and J are free index. So Gij is the second order tensor. That's the square root of this second order tensor is, you can write down the square root of E1 dot the second order tensor dot E1 minus 1. That's what we want. You see, the normal strain. The normal strain, finite strain, okay, in this E1 or X1, capital X1 direction. This is, we want to show this. You see, we want to show this. You see, this is, in this case, L E1. So this E1 dot G dot E1, you see, E1 is a vector 1, 0, 0 times the second order tensor G times E1 is 1, 0, 0. So this 1, 0, 0 is a transpose of 1, 0, 0 over here. So let's do it. You see this. Now don't forget, this is a 3 by 3 matrix. This is 3 by 1. So the result, when you multiply here, it is 1 by 3. 1 by 3 times 3 by 1 is a scalar. Don't forget this. This is a scalar quantity. Scalar. See? Now let's do this product over here. So now this first row times this column. So this will be, let's write here. You see? This is 3 by 1, the column. You see? 3 by 3 times 3 by 1 will be 3 by 1. Now, this is G11, G11, you see? Now, the second row times this column. So this will be G21, you see, G21 and G31, G31. Now let's do this product here. You see, this product here, or this, in this case, transpose unit vector, this will be easy. You see, now this is 1, 0, 0. You see, this is 1 by 3. This is 3, this is 1 by 1. So this is scalar. It's clear this is G11. Okay? This dot product of E1 dot second order tensor G dot E1 will be G11. So L E1 is equal to square root of G11, you see, this is G11 minus 1, you see, clearly. So this is a normal strain in this direction. Obviously, analogously, L, let's put L E2 will be square root of G22 minus 1. And L E3 will be square root of G33 minus 1. Don't forget that Gij is equal partial of xk, xi, xk, xj. Don't forget this. So G11, you see, this will be 1, this will be 1. You have to sum this a dummy index 1, 1 plus 2, 2 plus 3, 3. This is G22, we put 2 here and 2 over there. So that's clear. We solve this B, the section B. Let's start of this relation here. Don't forget, this is L square minus L0 square. You see, L is the length in the deformed configuration, and L0 is the length on this undeformed configuration. So this will be now L square, we already did this. You see, don't forget that L square is dx dot dx. You see, this is just quickly, this is f, let's put here, f dot dx, you see, dx f dot dx. Now transpose dot f capital X, you see, this is equal, now this is dx transpose f transpose dot f times dx. You see, this is G. Don't forget this. This is the second order tensor G. F is the deformation gradient. Okay, by the way, J here, you see, is the tensor, this tensor, a displacement tensor. Material. Why material? Because it's capital XJ. You see, look, G here was written in terms of material configuration. Now, L square is just this. Now, look how it's easy to see this. L square minus L0 square, this will be, you see, dx, let's put here, dx dot G dot dx minus L0 square, this will be dx square. And don't forget that dx square is equal L0 square. This will be, this is a scalar, dxi, dxi. What is this? This is dx1 square plus dx2 square plus dx3 square. Now we can put this in terms of delta ij. I can write dxi, dxj, delta ij, because delta ij, that dxj is dxi, so it's quite easy. Then we can write over here that L square minus L0 square will be, you see, this is dx dot G dot dx minus dx square. So I can write over here dx dot dx. This is equal. Now I can write here dx dot G dot dx minus dx dot dx, and I just put I over here. See, that's the same. That's an identity tensor. You see? Now L square minus L0 square is equal. Now dx dot G minus dot dx. I'll just write over here I. See how it's easy? Now, by definition, that's right over here. That's I will raise here. By definition, you see. Now, by definition, G minus I is equal 2 times L, the Lagrangian tensor here. I'll put just I over here. See? By definition, you see this right here. By definition. You see? Then L is just 1/2 of G minus I. Or you can write G is equal to L plus I. You see? Plus I. That's the G. Now, you see, we can come back to the item B and write, I'll write here, and we can write just easily, I don't know if you remember, but L of E1 is equal to square root of G11, you remember, minus 1. I can substitute G11 by this right-hand side over here. So this will be L is equal to square root of G11, in this case, will be 2 L11 minus, this case, plus 1 minus 1. Don't forget this, because G11, you see, look, that's for you to remember. what we wrote. You see, L11, that's right here, Lij is equal Gij, in this case, plus delta Ij. You see, because Gij is Lij, that's right over here. We define, you see, I'm sorry, this is a 2L, see, it's right now. You see, 2L plus I. In this case, that's right here. This is minus over here. See, the definition. See, you define 2L G minus I. Now, for I is equal J, 2L Ij is equal Gij minus 1. You see? Because for I is equal J, delta 1, 1 is 1. For I, different from J, 2L Ij is equal just Gij. Because for I, different from J, delta Ij is 0. Then here, G11, I is equal J is equal 1. So this will be, in this case, G11 is 2L11 plus 1. You see, this minus 1 here comes then out of this square root symbol over here. So this is L E1. You see? Like, for instance, L E2, this will be 2L22 plus 1. Because I is equal J, delta Ij is 1. L E3 will be square root of 2L33 plus 1 minus 1. Now, from the definition, you can write Gij minus delta Ij is equal to Lij. So Lij is equal 1/2 of, in this case, Gij minus delta Ij. And see, this is a chronic delta. You see? Now we can write this 1/2 of, that's right here. What is Gij? Remember this partial xk respect to capital Xi. This is partial xk respect to xj. This is Gij minus delta Ij. Now, we want to express Lij in terms of this displacement tensor, partial Uy respect xj, partial Uj respect xi, plus this is called a nonlinear term. Okay, let's express this from here. We can write. You see, that's very important for you to come back from the definition. I don't know, I'm sure you remember, you must remember, okay? This is x, this is dx, the vector. This is, let's call this is a vector over here. This is called d small x over here, okay? Now, in this, let's put a capital X is there, okay? Now this is U, okay? This X here, X plus the displacement is equal to the spatial coordinate. This is spatial coordinate, okay? Related to the deformed configuration. This is a vector X, okay? The position vector with respect to the undeformed configuration, and U is the displacement vector. Okay. Now from here, you see, you can express U. Let's put here, for instance, UK is equal now XK minus capital XK. Now, you see, or if you want, xk, let's write here, is equal, in this case, uk plus capital xk. Now let's take the derivative, okay, of partial xk, derivative of partial derivative of xk respect to xi. So this will be partial of xk with respect to capital xi. Because I want to substitute over here, this is equal. Now the displacement, you see, partial of uk respect to xi plus, in this case, partial of xk with respect to xi. Now, an important issue here is this. Look, x1, you see here, let's put over here. x1, x2, and x3, they are the coordinate, the material coordinate, you see, capital X1. And they are independent. That's why partial x1 respect to x1 will be 1. Partial x1 respect to x2 will be 0. Partial x1 respect to x3 also be 0. Like partial of x2 respect to x2 will be 1. Partial of x2 respect to x1, this will be 0, and so on. So it's clear that this is delta ki. You see? This is delta ki, because when k is equal I is 1, when k is different from I is 0. So we can substitute on the same analogously partial xk respect to xj, this will be partial of uk respect to xj plus delta kj. You see, it's easy, because when k is equal j is 1, when k is different from j is 0, this will be partial xk respect to xj. You just put here j over here. See, j and j and j. So, you see, now we can substitute over here and develop to come up quite easy with this. So Lj will be 1/2. Don't forget that this over here, you see, is partial of xk with respect to xi. You see, just over here. And this one is partial of xk respect to xj. And don't forget to subtract. You see, this is subtraction of delta ij. You see, minus delta ij. You see? Now let's develop this relation over here. I will raise here. And let's develop. It's quite easy. But remember about the property of the chronic delta. You see? Now let's do this. Let's multiply. This will be 1/2. Now, you see, partial derivative of uk respect to xi times partial of uk with respect to xj. This times this. Plus, now, this term times delta kj. Now, partial of uk with respect to xi, in this case, times delta k, this times this, and this times this. Delta kj. You see? Now, this one over here now times this plus delta ki partial of uk with respect to xj, now plus delta ki delta kj. We have 1, 2, 3, 4 terms. This multiply this and this, it's 2 terms. And this, multiply this and this, it's 4 terms. But don't forget delta ij over here. You see? Now we can see clearly the property of delta, Carnot delta. You see this, you see delta ki, delta kj. So this I comes in this place over here, so this is delta ij. And then this will be cancel. You see? Cancel over here. Now let's apply the property. You see, delta kj uk. Now you can see this is a partial of u respect to xi. You see, delta kj uk. So this will be j over here. Now, delta ki uk. So this will be partial of ui respect to xj. It's ready. Now, you see, Lij is equal just what is written over there.